Hi everyone. In this lesson we're going to continue our discussion of series and convergence. Now just a quick review here. Remember, an infinite series was something that looks like this, where we're adding up an infinite number of terms. So for example, if we have something like, so what we're doing here is we have our function a of n, and our indexing variable n goes from 1 to infinity, and we just put in the first term 1 in for n, and we get 1 over 1 squared. Then when we put 2 in for n, we get, and when we put 3 in for n, and 4 in for n, and so on. Now sometimes these terms will add up to a finite number, in which case we say the infinite series exists or converges, and sometimes it won't. Now if you remember last time, we looked at a particular infinite series called the geometric series, and that was defined like this. And this is where r is a number between -1 and 1, except for 0. And now for this series, we found out that it actually converged to that quantity. And the way we did that was by looking at the nth partial sums of this quantity, and we found that the limit of the nth partial sums was equal to 1 over 1 minus r. Once again, remember the nth partial sum is defined to be this quantity. Okay, so that's our nth partial sum for the geometric series. So you notice we only sum from 0 to n, and we found that this was equal to, and as n goes to infinity, you notice this term goes to 0, and we end up with 1 over 1 minus r. So we discussed that last time. Let's take a look at a few examples now involving this. So for example, what would be the summation like this, 3/4 to the n power. So remember, that is equal to, let me give myself a little more room here, that's equal to and we just continue like that. Well, all we have to do is use our formula for our geometric series up here. Remember this sum to, and we just plug 3/4 in for the r. So this will sum to, and then just simplifying this, 1 minus 3/4 is 1/4, and we get 4. And so that's our answer. So all of these numbers, when we continue this to infinity, we do actually get a finite number back, and it's equal to 4. Now let's take a look at a slight modification of this geometric series. Instead of starting our indexing variable at 0, sometimes we want to start it at 1. So what would our series sum to in that case? So if we have something like this, now still our r is going to be between -1 and 1, excluding 0. Actually, in this case, 0 would be okay. Let's see, so what is this going to equal? And we would just continue like this. Now if we compare this to what we have up here, notice the only thing we're missing is 1. So we see that this series is just equal to this one minus 1. Just take away the 1. So this is equal to the sum from 0 to infinity. And remember, this is equal to 1 over 1 minus r. And now simplifying this by cross multiplying, think of this 1 here as being 1 over 1. and cross multiplying, what we end up with is this. And simplifying that, you notice how these ones here cancel. Negative of negative r becomes positive r, and we get like that. So we have these two results then. And this one. And technically for this one it is okay to have 0 in for the r. We don't want 0 in for the r in this case because the first term would be 0 to the 0 power then, which would be an indeterminate form. So real quick example here. What would be, well, okay, so we're summing from 1 to infinity. The r is the 3/4 here, and so we just have to put 3/4 in for this term right here, and we get, and simplifying that and canceling these 4 terms right here, we end up with just 3. Alright, so that's the sum of 3/4 to the n as n goes from 1 to infinity. Now let's take a look at a theorem in our textbook that's going to be useful for us. So Theorem 9.7 is an important theorem for infinite series. It's very similar to the limit theorems that we've had before with respect to the limit of sums and differences of functions. But here we have the sum and difference of series. So the first one says that if you have a series involving the term c times a sub n, now the c is a constant here that does not depend on n, then what you can do is move the constant outside, so you can actually write this as, and this term we're assuming sums to a up here in the statement of the theorem, and we get c times a. So number 1 here says basically you can move the c outside the summation symbol, just like we did for limits. The second one here, let me elaborate on this a little bit. This says you can actually distribute the summation symbol very much like the way we distributed the limit. So in other words, you can write this as, you see how I distributed the summation symbol. And then in the statement of the theorem, we assume that the a's sum to capital A, the a sub n's sum to capital A, and the b sub n's sum to capital B. So this is a plus b. And the same thing for the difference. We would just replace the plus here with a minus and a minus over here. Alright, now let's take a look at an example that utilizes this theorem. So just off to the side here, let's consider this problem. So let's try to evaluate this. So we have the sum from n equaling 0 to infinity of 2 to the n minus 5, all of that over 6 to the nth power. Now what we're going to do is we're going to take this and algebraically manipulate it and use Theorem 9.7 along with the geometric series results that we had previously. So let's write this as follows. Let's write it as, we're going to break this fraction apart and write it as now we have two separate terms here, so we're going to invoke part 3 of Theorem 9.7, and let's write this, we're going to distribute the sum and write this as, now notice that 2 to the n over 6 to the n, we can write that as 1/3 to the n, And this 5 over 6 to the n we can write as... Oh, and I forgot to distribute my summation. I wanted to distribute my summation a while, so let me do that here before I write that 5 over 6 to the n. So all right. Now, this part right here looks just like a geometric series with r equaling 1/3. And this part right here looks like a geometric series, but we have this 5 here. Well, what we can do is we can move this 5 outside the summation by invoking number 1 right here. You notice how we move the c outside, where c is a constant. The 5 does not involve any n's, so we can move it outside. As long as this term does not involve any n's, it's a constant, it can be moved outside the summation. And so what we can do is move that outside. So let's just do that. We'll just take it, I'll erase it here, and I'll just move it outside. So right there it is. So then what we have is the first one is a geometric series with r equaling 1/3. So we can write that as... So that's what it will sum to, and that's because we're starting at 0. And the second one here I've got 5 times, and this is a geometric series with r equaling 1/6. And so that's going to be... And then simplifying all of this, 1 over 1/3 is going to be... And this is going to be 1 over 5 times 1 over 5/6. And then what we get here is, let's see, this term here is going to be 3/2, flipping the fraction up. These two 5s right here will actually cancel, or if I think of this term right here as being 6/5, when I flip the fraction up, you see these 5s cancel, and we end up with just 6 right here. And then just simplifying this, let's see, 6 is 12/2, so 3/2 minus 12/2, and we get -9/2. And that's our answer. So that's what this original series up here summed to. And now let's take a look at something called a collapsing or telescoping series. So let's consider a problem like this. Suppose we want to evaluate... Alright, so we have the sum from 1 to infinity, 1 over n squared plus n. Let's write this, doing a little bit of algebra, as follows. So we just factored out an n from the denominator. Now what we're going to do is try to use the partial fraction on partial fraction technique on this, and we're going to try to write it like this. Alright, so using partial fractions, we're going to try to figure out what the a and b have to be so that this equals the right hand side. Now remember what we do here, we have to find out what the a and b are, so we cross multiply this. And now for the left and right hand sides to equal, what we need then is that we need this to hold true. You see, we need the two numerators here to be equal to each other. So now we have to solve this equation for a and b. So remember what we did before. We just picked some strategic values for the n here. And so let's let n equals 0. That'll get rid of the an and bn term here and just leave us with the fact that a has to equal 1. Okay, so now we know that a is 1. And so then this equation becomes... And now let's pick another value for n, like a nice easy value, like how about 1. And then that will imply, we'll notice these ones here actually cancel. I could have done that. Get 0 over here. And then that will imply, if I put 1 in for the n, that b equals -1. Alright, so going back to our series now, we can write this term as follows. So we can write it as okay, so here we go. Now what we're going to do is this. Let's write out a few terms here, and we'll see that we get a lot of cancellation going on, and we'll be able to figure out what the sum is based on that cancellation. So if I put 1 in for the n first, notice that I get, okay, so this is when n is 1. Then if I put 2 in for n, I get, and let's just do a few more of these. If I put in 3 for n, and so on. Now we see what's happening here. You see how we have cancellation here. This 1/2 cancels with this one. The 1/3 cancels with this one. The 1/4 would cancel with the next term, and so on. And so we see that this series is just going to sum to the very first term, which is 1. Now that's our answer. There's a little more to it than that, actually. If you look in your book, you'll notice that your book does it like this. They actually evaluate the nth partial sum. So if you notice here, this term right here was when n was 1. This term was when n was 2 and n was 3. Okay, so you notice here that I'm just going to erase that term right there. So you notice the third partial sum, S3, would actually equal 1 minus 1/4. Okay, so in general then the nth partial sum is going to be 1 minus 1 over n plus 1, you see. See how the 3 and the 4, n and n plus 1. And so what we have then is the limit as n goes to infinity of our nth partial sum. That's going to be 1 minus 1 over n plus 1. Well, you notice this term just goes to 0, and we end up with 1. And so that's what this series sums to, because the limit as n goes to infinity of your nth partial sum is 1. Now, normally you don't need to do this down here for the problems that we'll encounter. You can just, normally the leftover terms out here are going to be going to 0 as n goes to infinity. And so you just need to find the terms at the beginning that don't cancel out, and that's what your answer is going to be. Let's take a look at one more example involving a collapsing or telescoping series. Let's take a look at this one. Alright, so we're going to do the same thing here. Let's try to incorporate partial fractions here. So we're going to write this as, and now we're going to try to write this term, the an terms, as follows. Now we have to figure out what the a and b are, so we'll cross multiply here and we get now we set the numerators equal to each other. We set those two terms equal to each other, and we have to figure out what the a and b are. So we set and now if n is equal to 1, or let's start out with 0 rather, that will imply that 3a equals 1. So I would just get 3a equals 1. These terms would go to 0. And I get 3a equals 1. So a is 1/3. So putting 1/3 in for the a and picking another value for n, let's see, we'll get, now a is 1/3, so this is going to be 1 equals 1, so these ones we could cancel those. Now if I pick n equaling 1 then, what I'm going to get is, I'm just going to cancel these ones here, put a 0 over here, and then we're going to get, and if we let n be 1, we get 1/3 plus b equals 0, and so we get b equals negative 1/3. Alright, so we have these two, our a and b. Put them in place, so we'll rewrite this sum as follows then. And now what we're going to do is we're going to just factor out a 1/3 here and move it outside the summation. That's using the first part of Theorem 9.7. So we're going to write this as okay. And now this is going to collapse. Let's write out a few terms and see how far out we have to go to see the collapsing taking place. So this is going to be, now we're going to have our 1/3 out here, and then we're going to have, okay, now if n is 1, if I put 1 in here for n, I get, now if I put 2 in for n, I get, alright, I don't see any collapsing yet, so let's keep going. If I put 3 in for n, we get, okay, don't see any collapsing yet. If we put 4 in for n, alright, now we see some collapsing. See the 1/4 cancel. And let's just do a few more terms here. So if I put in 5, I get 1/5. And so now you see the 1/5 cancels here. And we'll do one more term if when n is 6. When n is 6, 1/6. And we see that this cancels. Now we can see the next term is going to be when n is 7, 1/7 minus 1/10. And then plus ... then it'll keep going. Now you notice the 1/7 here cancels with this one. Now we see we've got complete cancellation on this term here, and the 1/8 would cancel with the next term, and so on. So now what terms out front here are left over? Well, we've got our 1 and the 1/2 and the 1/3. And then from there out, everything will collapse. And so our summation then is going to be, and that's what our answer is going to equal. And then we just have to simplify that. Let's see, common denominator here, 1/6, so this is going to be 1/3. I'm just finding a common denominator here quickly. So 1/3 times 11/6. And you get 11/18. And that's what this series up here will sum to, 11/18. And now let's take a look at another result that comes in handy. And this is Theorem 9.8 in your text. It's looking at the limit of the nth term of a convergent series. So we have this result. If the series of an converges, then the limit as n goes to infinity of the an terms must be 0. So here's a little proof of that fact. Let's just take a look at the proof of this, and then we'll look at a different version of this theorem that we actually use more often than this theorem as it's written here. So the proof goes like this. If you start out with the summation of your ANs, suppose that this quantity is equal to L. Then what that means is the limit as n goes to infinity of your nth partial sum is equal to L. Now keep in mind your nth partial sum is, you just add up the terms to the nth term. That's the nth partial sum. And I have an A1 here written. If this were the sum from 0 to infinity, I would have an A0 here first. Okay. So the limit as n goes to infinity of this quantity must be L. That's what we define the infinite series to equal. It's the limit as n goes to infinity of the nth partial sum. Now notice that if we look at Sn minus Sn minus 1, well let's first of all notice that Sn minus 1 would be now if we look at Sn minus 1, the only term that's going to be left over is this last one right here. And so what we get is that An equals, and now if we take a look at the limit as n goes to infinity of the An, we can write it as Alright, now this quantity right here we know is equal to L, and this quantity right here is also going to be L. You see, the Sn minus 1, if n goes to infinity, so does n minus 1. It's just the previous term. If n is 1,000,000, n minus 1 is going to be 999,999. It's just going to be the prior term. But as n goes to infinity, so does n minus 1, so this limit also has to be L, and we get 0. So that proves the fact that if your series involving the An terms converges, then the limit as n goes to infinity of the Ans must have been 0. Now the way we usually use this result is not as it's written here. We usually use what's called the contrapositive. The contrapositive of this statement would be if the limit as n goes to infinity of the Ans does not equal 0, then the series could not have converged. And that's written down here in Theorem 9.9. Let's take a look at that, how it's written, and we'll talk about that a little bit more. So here's Theorem 9.9, and it's just a different way of writing Theorem 9.8. So it says if the limit as n goes to infinity of the Ans does not equal 0, then your series could not have converged, so it must diverge. If you think about it for a second, so that's called the contrapositive of Theorem 9.8. If you think about it, if I make a statement like, if I'm washing my car, then it is sunny outside. So if I'm washing my car, then it is sunny outside. Now if you think about it, that's the same as saying if it is not sunny outside, then I'm not washing my car. Think about that for a second. If I'm washing my car, then it is sunny outside. That's the same as saying if it's not sunny outside, then I'm not going to be washing my car. These are the same statements. They say the same thing. So you see, Theorem 9.8 said if your series converged, then your limit had to be 0. So now we're saying if your limit's not 0, your series could not have converged, so it must diverge. So this is saying the same thing as Theorem 9.8 is. Now here's how we use that. Let's take a look at this quick example. So let's determine if this series converges or not. Okay, so the series n equaling 1 to infinity of n plus 1 over n. Does it converge or not? Well, these are the an terms. If we look at the limit as n goes to infinity of the an terms, you notice that this is equal to 1, which does not equal 0. Therefore, this series, by Theorem 9.9, it must diverge, so it does not exist. So therefore, our summation diverges, which is the same as saying it does not exist. Okay, so that's how we normally use this theorem. It's normally used as a test to determine when a series diverges. Now, keep in mind one thing. This is very important to note. Just because the limit of the ANs is 0 does not mean your series actually converges. So if I look at a series like this, so the sum from 1 to infinity of 1 over n, so that's 1 plus 1/2 plus 1/3 plus 1/4, and so on. This is a very important series. Now, you'll notice that the limit as n converges to infinity of the an terms is 0. But this does not imply that this series converges. In fact, it actually diverges. This series does not exist. It actually diverges. And we'll prove that later on. We're not in a position to prove that right now. But my point is that just because the ANs may converge to 0 doesn't mean your series converges. If you think back to Theorem 9.8, it's only making this statement. Theorem 9.8 is telling you that if your series converges, if it converges, exists, then the limit must have been 0. It doesn't say if the limit is 0, then it converges. And that concludes our discussion for section 9.2.